This video clip is for us to take a moment to look at a concept in kinetics or rates of reaction known as reaction mechanisms. Thus far in rates of reaction, we've been focusing on things such as reactions such as A plus B goes to C plus D, and representing the reaction with the progress of reaction diagram such as we see here. Now, actually, this is an oversimplification in both cases, where our reaction and our progress of reaction diagram for many reactions are not quite this simplistic. Many reactions actually proceed through a series of steps where reactive intermediates are created, and then we end up with the final product. We have our reactants, our A and B, and our final product appear in the last step. If we combine all these steps together, we get our overall reaction that we saw earlier of A plus B just goes to C plus D. Reactions typically go through several steps where we create things known as reactive intermediates. In this case, E and F are reactive intermediates, X and Y are reactive intermediates. A reactive intermediate being something that appears in our intermediate steps and then it gets consumed and disappears, leaving us with only the original reactants and the final products that actually appear in the final balanced equation. Another thing is that we draw a progress of reaction diagram for this mechanism, which takes 1, 2, 3 steps for the reaction to be completed. We'll notice that we have 1, 2, 3 different energy of activations for each step that takes place. A and B react, and at this first juncture we would have E plus F located here. E and F react to make X plus Y, which then react to create our final product, C plus D. As in a normal progress of reaction diagram, the difference here between where we start and finish still represents our overall heat of reaction for this particular reaction that's happening. So now what a mechanism is a series of steps. In this case, we have our first step, second step, and third step that the reaction proceeds through to create the final overall balanced equation. Oftentimes in a mechanism we produce reactive intermediates, which are chemicals that get fleetingly generated as the reaction proceeds. It generates E and F. The E and F rapidly turn into X and Y. The X and Y turn into our final product, C and D. Now, mechanisms can be used for a variety of things. One of them is they can be used to verify a proposed rate law expression for a reaction. And they can also be used to understand the process that the reaction goes through to turn into product. In working with mechanism, there's a strategy that we can use to use mechanisms for our advantage of trying to figure out sometimes the order of a reaction or a specific rate law expression. It's a 3-step strategy. The first one is we want to identify what's the slow step in the reaction mechanism. Then the second one is we're going to use the slow, which is also the rate determining step, to write what's called a preliminary rate law expression. Then the last step is if in our preliminary rate law expression there's any reaction intermediates, we have to take measures to eliminate those reaction intermediates from the overall rate law expression. Now here we have a reaction for which there's a proposed mechanism. This be the mechanism proposed for this particular reaction. It's a 3-step mechanism. And we're being asked here to use this mechanism to determine the rate expression in terms of H2 and Br2, the 2 reactants in this reaction. Step number 1 is identify the slow step. Here, step number 2 is our slow step in the reaction. So check, we've identified the slow step in the reaction. Step number 2, we use the slow step, which is known as the rate determining step, in that whichever step goes slowest has the greatest impact on the overall rate of reaction, to write what's called a preliminary rate law expression. In writing a preliminary rate law expression, what we're doing is saying rate is equal to K, and we take our reactants that we have here, the Br and the H2, they become our chemicals, the Br and the H2, And then a unique thing for preliminary rate law expressions is that the exponents, or our orders here, come from the coefficient in the balanced equation for the rate determining step. This is unusual in that it's only for a preliminary rate law expression that we use the coefficients in the step that's the slow step to create what our exponents or our orders are going to be in what's called a preliminary rate law expression. So when working, once again, here we have our slow step. The coefficients in the balanced equation, or excuse me, the coefficients in the slow step, which is the rate determining step, become the exponents in our what's called preliminary rate law expression. These coefficients become the exponents in a rate law expression only when working with mechanisms. Once again, to repeat, we can utilize the coefficients in a slow step or any mechanistic step to become the exponents in what are called preliminary rate law expressions. This is a strategy utilized only when working with mechanisms. Our next step is we have to eliminate any reaction intermediates from our preliminary rate law expression that we have. To identify reaction intermediates, we need to look at the balanced equation and see if we have anything that appears in our preliminary rate law expression that is a chemical that does not actually appear in our final balanced equation for this particular reaction. Examining our preliminary rate law, we can see that the H2 does appear in our overall balanced equation for the final reaction. So the H2 would be something that we would not say is a reaction intermediate. On the other hand, the Br does not appear anywhere in our balanced equation. This identifies the Br as a reaction intermediate, and we now need to take steps to eliminate the Br from our preliminary rate law expression. To eliminate the Br from our preliminary rate law expression, we need to look and see if Br appears in any of the other reaction mechanism steps. We can see that in step 1, we also have Br appearing, and that step 1 is an equilibrium process. Now, when something's in equilibrium, we can say that the rate going forward is equal to the rate going backwards. We can write a preliminary rate expression for the forward process in step 1, where we can say rate is K1 times Br2 raised to the first power, once again using the coefficient in the balanced equation to provide us with the exponent, which we can do because this is working with mechanisms where that process is both permitted, allowed, and used as a strategy. Similarly, we can write a rate expression for the reverse process in this equilibrium, where rate is K minus 1. This indicates it's the reverse reaction, and Br to the square to this 2, because our coefficient here that we have in our rate, our step in our reaction mechanism is a 2, which gives us our exponent for this rate expression in our preliminary process. Now, because again, when something's at equilibrium, the rate forward is equal to the rate in the reverse direction, we can set these two rate laws equal to one another. So at equilibrium, we can say that the forward rate is equal to the reverse rate, and we end up with this expression setting the forward rate equal to the reverse rate for the first step in our mechanism. What we now want to do is mathematical manipulation. We want to isolate our term for Br, and once we isolate it, we can substitute in to our preliminary rate law expression, and that would allow us to eliminate Br from the expression. First step, let's divide by k to the minus 1, which will eliminate our k minus 1 from this side of the expression. Now in here we have a constant divided by a constant. Now it may seem kind of silly to say this, but a constant divided by a constant gives us a constant. So let's replace this with just an expression saying K. Actually, for now, let's keep these intact. Let's make our next step. Let's just get rid of our square. If we take this whole process here and square root it, we can get rid of our square over there. And now we have something where BR is equal to the entire left side of our equal here, which we can use to substitute in for BR and eliminate BR from our preliminary rate expression. Completing our substitution, we now have K over K minus 1 to the 1/2, BR2 to the 1/2. This has all been substituted for our expression for BR in our preliminary expression. Well, notice what this does. It eliminates the BR from our preliminary expression. Our next step, here we have K times K1 to the 1/2 over K minus 1 to the 1/2. Well, we have a constant times a constant divided by a constant. All those constants come together just to give us a new constant, which we can call K. Now that we've substituted out our BR, we have this for our preliminary rate law expression, where we have rates K times BR2 to the 1/2 times H2 to the 1. We re-inspect this to see if there's any other reactive intermediates that need to be eliminated from the expression. Examining the balanced equation for our overall reaction, we can see that the BR2 appears in this balanced equation, so the BR2 would not be a reactive intermediate. And we also have the H2 that's in our preliminary rate law expression that appears in the balanced equation. So the H2 is also not a reactive intermediate. Given that we have nothing in what was our preliminary rate law expression that needs to be eliminated because it's a reactive intermediate, this would now be our final version of a rate law that we've derived from our reaction mechanism. This then that we have, this is our rate law that we figured out using a reaction mechanism, and it's a rate law for this balanced equation that we have. And that's how we would use a mechanism to determine our rate law expression for a particular reaction.